Hello guys, this is An Pichan. Welcome to my mathematics class. Let's see the today's topic. Today's topic is binomial theorem. So very important theorem. This theorem was firstly discovered by Isaac Newton, Sir Isaac Newton, who was very cerebral mathematician as well as physicist of that time. Okay, so why we need? Let me explain firstly why we need the binomial theorem. So let me tell you also binomial. Binomial means an algebraic expression having two terms a plus b, a plus x, y plus b. Well, these are the binomial, right? Now we have to deal, okay, with the power of binomial. So here, power of binomial 1, let's say, very easily can expand. And if, okay, power of, okay, binomial is 2. This is also can be handled. A plus b also whole cube. Already you can expand. There is also no problem. Okay, a plus b raised to power 4. This also you can handle, okay, right? Firstly squaring and then again squaring. You can find out the value of a plus b raised to power 4. So not so problem. Now, problem starts when the power of binomial is very big. A plus b raised to power 10. If I write, then you can show off your hands. You can't do this one either. I can, okay, right? Without binomial theorem. So binomial theorem is the formula to deal with this, okay? Or to deal with this type of, okay, power of binomial, right? So here, so this is the expansion, okay, who can deal with any power of binomial, right? So today we will prove this theorem, okay? We are going to prove this theorem. We will prove this theorem with the help of principle of mathematical induction. So what is the principle of mathematical induction? It's mandatory to know before doing binomial theorem, right? So binomial principle of mathematical induction, here I have written. So what is the statement of principle of mathematical induction? Let's see. The principle of mathematical induction states that if P of n be statement, P of n be any statement, right? So like this, okay, this is the statement, right? Be a statement, and if P1 is true, means Pn is true for n is equal to 1, and Pm plus 1 is true whenever Pm is true, right? Then Pn is true for all n belongs to capital N. Capital N means set of natural numbers, right? The principle of mathematical induction is used if n belongs to capital N, means set of natural numbers, okay? This is the statement, right? So we need to show firstly P1 is true. If we use, okay, principle of mathematical induction, we need to show, okay, P1 is true, and then we have to suppose, okay, Pm is true, and then we have to prove Pm plus 1 is true. If all these two statements are proved, then we can say Pn is true for all n belongs to set of the natural number. Then we can say this theorem will be true for all n belongs to capital N, right? So here is for any positive integer, and positive integer n means natural numbers, right? Okay, so let's try to prove. How to prove? Uh, so now I think, okay, you are clear about the principle of mathematical induction. What is the statement of mathematical induction? Exactly using this statement, I will try to prove. For your kind of information, this topic I have taken from grade 11, and in some boards you may find out that in grade 12. So this is important, okay, for 11 and 12. Okay, for any positive integer n, this is this one. This is a statement. Let's suppose, okay, let Pn be the given statement. So what's our statement? This one is our statement. This is a whole is a statement. We can write on like this way. P of n such that a plus x raised to power n is equal to c of n 0, or you can say nc 0 a raised to power n plus C of n comma 1 e raised to n x and plus C of n comma 2 e raised to power n minus 2 x raised to power 2 plus dot dot dot. Here we may write down one more also, ncr e raised to power n minus r x raised to power. I have a dropped, okay, no need while proving, okay, while proving here, see, while proving this theorem, and ncn x raised to power 1. Very wonderful theorem, right? Okay, this is a statement. Let's check, okay. For n is equal to 1. For n is equal to 1, so left hand side. This is the left hand side and this one is the right hand side. Okay, this one is right. A plus x raised to power 1 is equal to a plus x, and right hand side, now you have to use n is equal to 1. So let's start with c of 1 comma 0 e raised to power 1 plus c of 1 comma 1, because you can go up to this 1 to 1. Just like if you have an n, then statement says, okay, n to n, okay, ncn. So if you have a power 1, then can move up to 1c1, right? So 1c1 e raised to power, here instead of n we have 1 minus 1 x, okay, is equal to, now let's see, 1 factorial directly also we can write down, okay, here 1, okay, so simply, okay, c and g and c0 is always 1 erased only 1 plus this is also 1 a raised to power 0x. Okay, so listen to me everybody, c of 1 0 is 1 and c of 1 comma 1 is also 1. So how we get, okay, if you don't know, then this formula we have used 1 factorial, 1 minus 0 factorial and 0 factorial. This one actually, okay, this one formula we use, okay, and factorial and minus r factorial and r factorial. Using this we can get 1 factorial and 1 factorial, 0 factorial is also is equal to 1. Full information I am going to provide you, so ultimately you get here 1. So for this also same, right? Now is equal to here a, you are getting, okay, here a plus here into, right? Okay, this also into you can say, and here 1 e raised to power 0 1 and x, okay, x. So equal, left hand side is equal to right hand side, you can say, therefore p n is true for n is equal to 1, for n is equal to 1. One step is completed, right? One step is completed. Now we have to suppose, okay, suppose second step, Pm is true for m belongs to n. So m is any or natural number, right? M is any natural number, for that also true. That is you can say a plus x raised to power m is equal to c of m comma 0 a raised to power m plus c of m comma 1. Instead of n you have to write down m, a raised to power m minus 1x and plus, okay, here I'm writing c of m comma 2 e raised to power, here m minus 2 x square plus dot dot and plus c of m comma m x raised to power 1. Let's say this one we use, okay, later. This is not so difficult but little bit lengthy, okay, except this. Okay, this we have supposed, okay, second step. Now third, okay, we have to prove, okay, Pm plus 1 is true whenever Pm is true. This is the last step of mathematical induction. Here, okay, we now, okay, or we shall prove that Pm plus 1 is true when Pm is true, or Pm is true, okay. That is, we prove that, let's see, okay? We prove that a plus m, sorry, here x raised to power m plus 1, because now we have to show pm plus 1 is true, okay, is equal to c of m plus 1 comma 0 a raised to power m plus 1 plus c of m plus 1 comma 1 a raised to power m plus 1 minus 1 x and plus c of m plus 1 comma 2 e raised to power m plus 1 minus 2 and plus dot dot. Okay, final step, final term, m plus 1 comma m plus 1 x raised to power m plus 1 here, m plus 1. Okay, let me just write down again. Okay, and plus c of m plus 1 comma m plus 1 x raised to power m plus 1. So again, okay, now you will understand. M plus 1. Now we want to prove this one. Alright, finally, I think okay, you understood here. M plus 1. Now you have to replace m by m plus 1. Now with the help of this we have to prove. We shall prove that pm plus 1 is true when pm is true. That is, we prove that. What we have done here, we have replaced n by m plus 1. So m plus 1, m plus 1, m plus 1. Each and every n we have replaced by m plus 1. Now we have to prove, okay, this statement. Now we have to show left hand side is equal to right hand side. Okay, this is the final step of your principle of mathematical induction. If this goes true, then we can say the whole statement is true for n belongs to capital N. I mean to this set of natural numbers. Okay, now let's take, okay, left hand side. So we have here left hand side a plus x raised to power m plus 1 by using the law of indices, or we can say here a plus x into a plus x raised to power here. Okay, 1 minute. Let me write down here m into a plus x. And a problem? No problem, right? So this I'm writing here a plus x here, right? A plus x. Now let's put the value of a plus x raised to power m. Where is value of a plus x raised to power m? Here. A plus x raised to power m is here. Now let's use, okay, let's substitute, okay, the value of a plus x raised to power m here, right? So we can write down here, I'm using, okay, with big bracket, c of m is 0 e raised to power m, this is length line here, m comma 1 e raised to power m minus 1 x plus, okay, dot dot, and here plus c of m comma 2 e raised to power m minus 2 x square plus dot dot here not dot, okay, plus, okay, here this is a plus, this one and this, and here we have, okay, m comma m x raised to power m, big bracket close. Only just, okay, here I have done a plus x I have written here, and the value this I have taken, okay, from first, okay, a plus x raised to power m. Here also I am writing, okay, using first, okay. From where I have taken this, so you can, if I write here using first, it's clear, okay, we have used the first. Okay, now after that, okay, you have here, you have to multiply. This is the E length, a little bit lengthy, okay, right? So sometimes, okay, you get bored, okay, all right. So lack of space, okay, I'm just breaking the symmetry. I'm writing, okay, from here because I need, okay, big space. I don't have here so big space. Okay, so you don't need to write like this way. Actually, we should not break the symmetry, right? Okay, here a plus x, just multiply, okay. Okay, just multiply a times this, just ordinary multiplication, a times this, what you will get, see very carefully, c of m comma 0 e raised to power m plus 1, law of indices, here a having one power, a into a raised to power m means a raised to power m plus 1 plus c of m comma 1 a raised to power m simply x, right? Because we are e raised to power, and then plus uh, c of m comma 2 e raised to power m minus 1 if you multiply with this x square plus, okay, dot dot, and you write down here c of m comma m x, okay, raised to power m a, right? So I'm putting in one bracket. It will be easy to understand because this shows that, okay, you have multiplied by a, and then plus, now start by x, okay, x into this c of m comma 0 e raised to power mx, okay, and plus this into this, and c of m comma 1 e raised to power m1 x squared. Now it's on plus c of m comma 2 e raised to power m minus 2 x cube, okay, x cube, and plus dot 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 c of m comma m means mcm x raised to power m plus 1, right? M plus 1, and yeah, this was, okay, last one. Okay, so let's close the bracket. Now we have multiplied, right? Now we have to collect, okay, right? Okay, we have to simplify. So how to simplify? It's very simple. First term you write on the same way, c of m comma 0 e raised to power m plus 1, because you will not get another this term, right? Because all have x here x, so everywhere you will get, okay, x, right? And last term will be the e, okay, same, okay, this one, because you will not get any term having, okay, x without a, right? So this is also, okay, I mean to, okay, single x, right? Otherwise, okay, you will get ax, right? Here, okay, you will not get x, okay, here you will not get, okay. So this is the first term, this one is the last term. Okay, let's simplify the terms between first and last, okay. Here, a plus x, a raised to power mx, let's find out, okay, a raised to power, yeah, here, okay. Look at here, this one and this one, right? Here, okay. So first e raised to power mx here also. So we can write down here common, right? E raised to power m, c of m comma 1, right? And plus c of m comma 0, and here common is e raised to power mx. No problem. And the next one, let's find out, okay, here, yeah, this one, these two, you will find out like this pair, right? So this one is, and this, and these two, right? These two. And let's take, okay, common here also. You are going to get common. So very easy. M2 and plus C of M comma 1. And into, you will get here, common is this one, e raised to power M minus 1, x square, right? So here, this into this. Okay, lack of space. I'm compared to write here. And all right, and if you want to next, all right, so mx, all right, so otherwise, okay, you can write now dot dot dot, because here I have not written one more step, so this is not going to be. And similarly, okay, the process is right going on similarly, dot, and let's write on the final term. Final term is this one, c of m comma m x raised to power m plus 1. Okay, now no problem. Now you understood, okay, see very carefully how we have done here, right? So if you have a problem, you can tell me. Okay, now any space, I'm going to erase this side. Now I'm going to expand here. Oh, very nice topic. Let's see. Here, listen to me very carefully. C of m comma 0 is equal to 1. You can check yourself. And also C of m comma m is also 1, right? So instead of, okay, I'm going to write only 1 simply. 1 times e raised to power m plus 1, and plus See here very carefully this step, and I'm going to make like this way, C of m comma 1 and plus C of m comma 1 minus 1. Later I'll explain, okay, what I've done. Okay, 1 minus 1 is 0. I had a problem. And plus, here also C of m comma 2 plus C of m comma 2 minus 1 you can write down into a raised to power m minus 1 x cube plus dot 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 plus here this is also 1 x raised to power m plus 1 as I've written here, right? The C m comma m is also 1, right? So I think you understood this line now. I'm writing okay this side. 1 again I'm going to change, okay, 1 we can write on C of m plus 1 comma 0 a raised to power m plus 1 because okay value of this also 1. C of m plus 1 comma 0 also 1, that's why, okay, instead of 1 I have written 2, okay, yeah, make similar 1 same 1 here, and plus here I'm going to write down the formula. So which one formula in combination we have studied? C of n comma NCR plus NC minus 1, then we can write down, okay, C of n plus 1 comma R using this property. This is the property of combinations. I've also done in one video. You can go through that, okay, if you have problem. So see, using this I'm going to change this one. So okay, so now I think understood. Okay, so what's that? Okay, what you can write here? C of m plus 1 comma 1 you write down here a raised power m, right, and here x, and the next one plus here also you are going to change, okay, you can write on C of m plus 1 comma 2, and here you can write on e raised to power m minus 1 x square dot dot, okay, final also you will write on your C of m plus 1 comma m plus 1 x raised to power m plus 1, okay. So here no problem because value of this one m plus 1 comma m plus 1 also is equal to 1, okay. So here you have no problem, right? Now you will understand, okay, value of this also 1, that's why I've written, because to make, okay, same, okay, m plus 1, okay. Okay, now I think you understood. Let me tell you again. See up here, value of this also 1, e raised to power m plus 1, C of m plus 1 comma 1 e raised to power mx plus here, okay, using, okay, property as I told you, right, here also this. Here value of this also 1, right? Now you understood, here we have used, okay, property of combination, and here also we have used property of combination, right? Because value of this 1, and to make same I have written value of this also 1, okay, 1 I have converted in this form because to make same, right? Okay, so let's try to write on the final step. M plus 1 comma 0 e raised to power m plus 1, okay, we are getting right inside, okay. C of m plus 1 comma 1 e raised to power, here we can write on m plus 1 minus 1 because ultimately you will get, okay, m, and here x, okay, getting, okay, this one, alright, this second step also we got, okay, and then next one, okay, C of m plus 1 comma 2 e raised to power m plus 1 minus 2 because we will get, okay, here m minus 1, okay, x square, we got this one, and finally also we are getting C of m plus 1 comma m plus 1 x raised to power m plus 1, okay, exactly right inside we have a got here is equal to right hand side, okay. We can say, okay, this shows that Pm plus 1 is true whenever Pm is, okay, true, hence by PMI means principle of mathematical induction, Pn is true for all n belongs to capital N. Alright, so capital N and finally, okay, hence, so if you want to write on the last, okay, now you can say for any positive integer n, a plus x raised to power n, this, right? Positive integer mean a natural number, right? Set up natural number, no problem, okay? So now I think I understood. Clear? Now, now let's see here. Now we can write down, okay? Note down. So we have a plus x raised to power n is equal to c of n comma 0, a raised to power n plus c of n comma 1 and minus 1x plus c of n comma 2, a raised to power n minus 2 x square plus dot. Here one more you may add, okay, and c and cr x raised to power n minus r x raised to power r plus dot dot c of n comma n x raised to power n. Now this is a binomial theorem. So see, if here if x is equal to 1, then you are going to get, okay, 1 plus x raised to power n is equal to c of n comma 0 plus, because here 1, and this c of n comma 1 x, because here 1 having power means 1 here, and plus c of n comma 2 x square plus dot dot plus c of n comma r x raised to power r plus dot dot here c of plus c of n comma n, right? So you can write on like this also. If you use, okay, value of this one, you are going to get, okay, n factorial upon n minus 0 factorial r, sorry, here instead of r we have a 0 factorial plus here n factorial upon n minus 1 factorial 1 factorial, okay, x plus n factorial upon n minus 2 factorial, and you are going to get 2 factorial x square plus dot dot. Here you may write down, okay, n factorial upon n minus r factorial x square, sorry, x r plus dot dot, here n factorial upon n minus n factorial, and here, okay, n factorial. Okay, no problem. And is equal to, now here you may write down, okay, n factorial upon n factorial, 0 factorial is 1 plus n minus 1 factorial, you can expand this one, n minus 1 factorial x plus n minus 1 n minus 2 factorial upon here n minus 2 factorial 2 factorial. Okay, so here also you will write on 1 factorial. Actually 1 factorial is 1 x square plus dot dot, and here n minus 1 n minus 2 dot dot, here you may get, okay, okay, here no space, and this n minus r, okay, plus 1 into okay, n minus r factorial over n minus r factorial, here r factorial, okay, or like a space, okay, here okay, x raised to power r plus, and final term is this one, n factorial upon, okay, cancel, you are going to get, okay, 0 factorial, so 1 you are getting here, right? Okay, so what more, okay, I forgot to raise to power, here n x raised to power n, here x raised to power n, so here into x raised to power n you will get. So finally you are going to get, cancel 1 plus this cancel, and x upon 1 factorial plus, and cancel n minus 1 upon 2 factorial x square plus dot dot plus n minus 1 n minus 2 plus dot dot, sorry, only into the multiplication, n minus r plus 1 over this cancel, and here r factorial x raised to power r plus dot dot. Finally, you are going to get x raised to power n. Okay, this is the okay. This also we can write down okay from this theorem. All right. This is also okay, binomial expansion. Okay, everybody, and another one also we can write down if bx okay is replaced by negative x, then it becomes okay 1 minus x raised to power n is equal to 1 minus nx upon 1 factorial plus n minus 1 2 factorial x square minus dot dot okay plus this minus 1 here okay, here minus 1 raised to power r also you will get, and plus dot dot minus 1 raised to power n x raised to power n you will get if you replace okay x by negative x, otherwise okay so okay so this expansion also we can write down okay by using this okay we have derived okay from here, only just we have used the just use the formula for combinations. We have used we have just okay find out the values of Cn0, Cn2. Okay, we have expanded okay by using the combination theorem, right? So very easy, we can find out easily. So I think now you understood okay how to prove very nicely. We have proved binomial theorem. Binomial theorem is very important. Now you understood okay. So you have no any questions, you have no any doubts. I think okay. If you have any doubt, so don't hesitate to write down in comment box. Okay, thank you very much for watching. Bye bye.